Welcome back. So, as far as I can tell, Roberto will now tell us about how you can tune your entity attribute value queries, or something more sane. Have fun. Roberto told me that he will upload the slides, so there will be no necessity to take pictures of any slides. Okay.
Is this on? Okay. Everybody hear me okay? Thank you. Well, it's nice to see everyone. Thank you all for coming. Nice big room. Well, my name is Roberto. I work for Snowflake, which is, I imagine, might sound a bit weird for a bunch of people, because Snowflake hasn't typically been on Postgres conferences, at least not the ones that I've been to. But I'll be talking today about Postgres 18, the performance enhancements that we're seeing, and hopefully all of you will experience very shortly. This is my email. I included the slides, the QR code. I didn't know that we had to upload, and Karen will help me later. Karen's my colleague. She's right there. She's awesome. So she'll help me upload it. But this goes to GitHub, and you can download them now. But I'll post them to the conference system as well, so that you don't have to remember to do that. But you don't have to take pictures if you don't want. So a little bit about me. I've been working with Postgres for a long time. I love it. It's a great product. I have a lot of fun trying to help people and companies, and spending a lot of time writing emails to them that they never read, or don't follow the advice. Karen's laughing because she knows it's true. So I've worked in different teams, DevOps, DBA. My alma mater is Utah State University in Utah. So I'm originally from Brazil. So any Brazilians in the room? No? I don't see any. Okay. So I was born in the Brazilian Amazon, in Manaus. I live in Utah, in the United States. I don't know how many of you have been to Utah, but it's a pretty place if you like mountains and skiing and snowboarding and nature. So there's a lot of it. But Europe has got such amazing places as well. But if you do make it to the U.S., stop by Utah, buy you a beer. Usually when I'm not doing work, I do more computer stuff, different projects, automation, whatever strikes my fancy. But I also like photography, snow sports, and Austrian economics. So I'm quite fond of reading about it and how it applies to freedom, liberty, and all. I'm currently a senior solutions engineer for Snowflake. There's my LinkedIn and my X profile. I don't have a Mastodon. And the reason why I mentioned the previous year for Crunchy Data is because a few months ago, Snowflake acquired Crunchy Data. So there's a blog post about it. So Crunchy was all about Postgres. That's all we did. We helped customers with all their Postgres needs in cloud, on-prem. And Snowflake they have their own database that was meant for analytical workloads, but they have since expanded into this whole data platform where you can move data around and you can have access controls around it, and you can query your data in easier ways, and you can run AI on it, all within the same platform. And a few months ago, they acquired Crunchy to bring Postgres into their set of offerings. So I imagine in a few months, you will see a Snowflake Postgres product. So you can run Postgres in the cloud or any cloud and interact with your Snowflake data and vice versa. Anybody use Snowflake? Okay, so we have a few. Okay, good. So I have a couple of my colleagues here for Snowflake, so reach out to them as well. So there's Celeste and Karen. But yeah, so Snowflake will have a Postgres product, and hopefully will be a more constant presence at Postgres conference and sponsoring. We'll see what happens. But what we're going to talk about today is how Postgres 18 introduces fantastic performance improvements. So some of them are pretty foundational for real-world query patterns. So there's a lot to cover. Some of it we'll be able to go through a little bit slower, and some of them we might go a bit faster. But there's a bit for everyone that uses typical applications, particularly ones that rely on ORM-generated patterns of query patterns. So I tried to come up with a set of benchmarks that would exercise these features. And I've seen a lot of posts around async IO especially that floated around. It's not my area of expertise, benchmarks, so I tried my best. I'll publish them, but I haven't done it yet. But I tried to come up with some benchmarks that would exercise these things with real applications, so we'll go through them. But we'll talk about async IO, B-tree skip scans, parallel gen index creations, query optimizers, explain, GUI DV7, and we'll show some real-world apps that come with that. So we'll start with the async IO. So traditionally, Postgres had sync IO. So the backend would ask for a page of data from the kernel and say, hey, give me this page. And the kernel would say, OK, we'll read it. And then the backend would be just sitting there waiting. We'd get the page and say, OK, give me another page. And then the kernel would say, OK, I'll read it. Here you go. So we'd do this synchronous pattern. So it was one request at a time. And the backend would be mostly idle, waiting for I/O. So improvements in hardware have made it so you can parallelize requests, and the synchronous pattern underutilizes that modern storage. So in Postgres 17, they introduced some read stream and vectored I/O APIs and some internal abstractions that paved the way for this Postgres 18 features. And Andres, I think it was 2 years ago, I think this was 2023, he did a talk in Prague where he talked about the difficulties and where he was going. And it took a long time, but I think we made it. But this is quite an interesting talk if you listen to it, if you have time, because it goes over the problems. So in 18, what we have is that we're able to spawn different workers, and we can request multiple pages of the operating system. So if the backend says, hey, I need all these pages, the kernel can queue all those requests. The backend can continue to do other work, and as the kernel returns those pages, as they're ready, the backend can process and complete them. So it can batch. The backends can now batch multiple I/O requests. The kernel can optimize how it orders those requests, and it can use those the better hardware, the storage features that are now quite common. And while the kernel was returning those pages, the backend can actually do useful work instead of just waiting for the data to come back. So it's quite an improvement, and I imagine we'll see more improvements based on this foundational work. To me, it's a great example of how Postgres has this iterative but very fast pace of improvement over time. So there are a few parameters that control that. So one main one, I don't think this, can you guys see this pointer? I think so. This IO method parameter selects which type of async IO will be selected. The default is worker, and there's another slide that talks about this as well. This one was introduced in 17, IO combine limit, and it's in blocks of 8K, by the way. So 16 blocks is 128 kilobytes. So remember that. So this was introduced in 17, and these two were introduced in 18. So this selects the type of IO method, and this is the maximum that you can get for the block of operations. So the max combined limit silently limits, I/O combine limit. So if you want to raise how much you want to get of data, remember to raise both. Because if you raise just one, and this one you can set per session, this one only at server time. So if you want to raise both. Otherwise, this one will limit that one. Max combine limit will limit combine limit. So the operations that are most benefited are sequential scans, because it's going to grab several different pieces of data at the same time. Bitmap heap scans with multi-index queries, and vacuum. And I think there's a talk from Melanie about vacuum. There's several other improvements on vacuum specifically that improve on performance. But I can't remember if it was today or if it's tomorrow, but I'm hoping to catch that talk. Oh, it's now? Okay, so I'm not going to catch that talk. But I remember seeing it on the schedule. Okay, so on my non-super professional tests, this is what I came up with. So sequential scans had 15 to 25%, bitmap 10 to 18, but vacuum had quite a bit of variability. So in some workloads it'd be 20%, some workloads would be 300%. So that, and I imagine the improvements in vacuum that others that Melanie is talking about freezing, made a difference in this as well. So this is not entirely async I/O, but this difference can be quite significant in PG18 for vacuuming. So typically, you should see improvements if you select async I/O, and if your workloads work well with that, which most workloads will, because most are read-only, or mostly reads. But how much would depend on your specific type of querying. So here's an example where we have some averaging and some counts from a table, a large orders table, and we do a grouping by a category. In 16, that ran as a sequential scan in 12 seconds, but in 18, it went down to below 10. So, and I basically I had no code changes at all. I didn't change my application. I didn't add any indexes, but just through the fact of being able to query those I/O operations several at a time, I was able to get an improvement. So, free performance improvement. Tuning for production. So, as you can see here, I'm doing a vacuum, and this is new in 18. You're going to see these I/O workers. That is, if you selected the worker I/O method, which is the default, and I'll mention that here. So there are 3 that you can pick for I/O method. You can use worker, which is the default. You can use IOU ring, which is specific to Linux, and it creates these async I/O queues on Linux. And the traditional, so if you want backwards compatibility, you go to sync. So obviously you wouldn't be using async I/O, you'd be using synchronous I/O. But here I have the worker method, and I'm running vacuum on a very large table, and I/O stat shows me that I have 5 workers, and they're all doing work at the same time. So they're all reading things at the same time. If you do the same on pre-18, you're basically going to see the backend handling that connection, doing the reads. You're not going to see all these processes here. So all of these are working at the same time and trying to queuing and getting data from the kernel. So I/O method, pick the one that works for you. I think I mentioned it, but in my tests, worker worked the best. Find out for yourself. I/O workers, the default is 3. It seems pretty low, especially if you have a lot of cores available. Remember, each one of these workers will translate to a process, a backend process. So probably set it to about a quarter of cores. Thomas has this very nice talk that I referred to it quite a bit during preparing this one, So go take a look at it because he has a lot more details. And again, combine, if you want to raise these, how much you're batching, raise both max combined limit and IO combined limit. And they're in blocks of 8 kilobytes. So on Unix, max combined limit, the maximum is 1 megabyte, which would be 128 blocks. And on Windows, the typical maximum is 128, which is already the default, which is 16 blocks. So use the method or test different methods, either worker or IOU ring, test the number of workers with the number of cores, and raise these as appropriate, and see where it takes your workloads. And read Thomas's blog post, because it's quite nice. So this is from Thomas's talk as well. He benchmarked the different methods and different number of workers and came up with a quite interesting distribution on this machine with 12 cores and 24 threads. So take a look at that. There won't be time for me to go over it, but it's quite interesting to see. On my test, I had a machine with 8 cores. I tried to separate one machine with applications, one VM with Postgres, and them talking over TCP/IP. And I had my Postgres machine at 8 cores. And then when I put 8 workers, I had a performance degradation sometimes. So adjust for that. Okay, so, well, kind of already talked over it. So increase IO workers, start with a quarter CPU cores, test. Bitmap scans benefit the most out of these, in my experience. Watch out for signal overhead between backends and workers, and file descriptor limits. If you have a big machine with lots of cores, make sure you don't hit the file descriptor limits or IO bandwidth saturation. So test and verify, basically. I don't think there's one single recipe that's going to tell you the right answer for everything. But there's a lot of tools. Okay, so that's async IO. SkipScan. SkipScan is quite interesting. So what a SkipScan tries to do, it gives us acceptable performance for queries that are not run very often. So typically when we're evaluating our workloads, we look at our table and say, oh, this query we're going to always query on this column or filter on this column. Let's create an index on that column or these columns, right? But sometimes you don't really query it or the requirements changed, and then you don't have an index on that column. And SkipScan is going to help you with that. So if you create an index on a column that you sometimes need to filter on, then you're always paying a penalty, right? Every time you write to that table, it's going to write to that index, but you only need to query it every once in a while, so you're paying a penalty, but not really getting that much benefit. What SkipScan will do is give you better benefit than a sequential scan, but not as great a benefit as a dedicated index. But it's way better than a sequential scan. So if you have a table here, orders, and you have a composite index on country and user ID, but you decide, or someone decided to run a query or requirements changed, and you filtered only on user ID. So before 18, you wouldn't use that index because it doesn't start with country. So we would fall back to a sequential scan, and it would be quite slow if that table was large. So the typical advice we would give would be, well, create an index on user ID. But if you're not using it very often, you're paying that penalty. So what SkipScan will do, it will treat that index, that composite index, as a series of logical subindexes. So the planner is going to recognize the opportunity to use that multi-column index, but for each distinct country, it's going to search for the user ID. So it's going to be most effective when your composite index the leading column has a low cardinality. So the example here, we have 10 countries, that's low, and we have 1 million user IDs. No, that's high. So in this example, we'd skip the we would do 10 targeted index searches and skip over the ones that we don't care about. So you would be faster than a sequential scan. So here's 16. I created this table called skip scan test, and I selected ID, project ID, and creator dat. But I'm filtering on creator dat. And I don't have an index on creator dat. I have an index on project ID and creator dat, so that it's a composite index. So on 16, we'd have these multiple workers that would be to do a parallel sequential scan and would filter at creator dat. And that would give me 466 milliseconds. But on 18, what it does is that it does an index scan on this composite index, and it does 1,001 index searches. So it skips over the ones that it doesn't need. So there's country and user ID, and I'm like, okay, sorry, it's not country. I'm using the wrong example. Yeah, project ID and creator dat. So you would treat the index as a series of logical subindexes and skip over the ones that it doesn't need, but finds the one that you need. So again, faster than a sequential scan, slower than a index scan, a dedicated index scan. So it's basically going to use that index and skip over the ones that it doesn't need, and it gave me quite a nice improvement. Without any changes, no new indexes, no analyze. So it's quite nice. So here's my test on range of queries and timeline queries. It was really nice. Distinct and filtered scans, not so nice. So it depends, right? Your mileage may vary. Check for your own workloads. Okay. Parallel gen. So gen indexes are generalized inverted indexes. They're mostly used for arrays, JSON-Bs, full text searches. So they can be slow to build on large tables. If anyone who's worked with lots of JSON-B data will attest. So higher maintenance work mem helps, but remember that vacuum also uses maintenance work mem. So if you need to build a large index or large indexes with JSON-B or full text, and you want to raise this, remember the vacuum we use it. So you should also limit how much auto-vacuum work mem will be used. So raise this, but also cap auto-vacuum. Otherwise, it's going to spawn all those auto-vacuum worker processes that might use too much memory. So Postgres 18 gives us parallel index builds for gen indexes. B-trees and Brin already had them. We have it on gen now as well. So if you have your max parallel maintenance workers set to a number greater than 1, and you decide to create an index on a gen on a column using a gen index, it's going to spawn these parallel workers for that index. And you can see here, I did a lot of watching IOStat run. I was running queries and I would watch IOStat, and it was quite interesting to see all these reads going on for all these different types of workers. So yeah, now parallel index gen builds. On my test, I had quite a bit of variability as well, and I mentioned this a little bit earlier. So I had 8 cores to work with, and sometimes if I put it to 8 cores, I had a degradation. And it depends on index type, I guess. So for JSON-Bs, I had an improvement. I don't know why 17 was worse than 16 on this test, but full text was quite interesting. And on different runs, I had different results, depending on the data. So again, you have to test. But array indexes was really nice on 18. I had another test that I think I forgot to include the figure, but I tested it with 2, 4, and 8 workers. So make sure you run some tests and find out what works best for your workloads, your own indexes. So the sweet spot for me was JSON-B and array with 4 workers. And so try to start with max parallel maintenance workers less than or equals to your CPU cores. All right, we got to optimizers. Optimizer has a lot of things, and the theme that I could identify was ORM queries. There's a lot of improvements for, I see, yeah. So the optimizer works better now with hash joins and group bys. It transforms large lists of in values that it basically took the improvements in 17 that it already did these transformations and combined with the new skip scan or clauses as well. It did this very nice self-join removal. You had speed ups on intercept and accept, window aggregates, view column aliases, and we had select distinct internal ordering, reordering to avoid sorting. And we'll go over them a little bit in detail. But most of these don't require you to make changes to your applications or to your queries. Most of them will just work. But I'll emphasize this. Please do test and verify. Because, you know, the world is a very, there's a lot of variability in the world. So test and verify. Okay, so in values, 18 adds the NB tree skip scan. So we mentioned skip scan a little bit earlier. Postgres 17 added this transformation that it could take a large N list of values and convert it to an any. But in 18, it's able to work with values that are both close together. So if you have 1, 2, 3, they're close, right? They're one after the other. And they all have to be scalar values, by the way. But now it can also work with items that are far apart. So if you have 10,000 and 20,000, they're far apart, but it can work with those. And it supports complex combinations of in, equals, less than, greater than, less than or equal, greater than or equals. And it only reads the index leaf pages that might have matches. So on this example here, I have this table, tab, and I have A and this list of 10 values, but I also am looking for B equals 5,000. So what it's going to do, it's going to convert this list to an array, then do an any on that array, and a B. And you can see here that it did 10 index searches. So it's going to skip over these 10 to find that 5,000 if it had a composite index. So it's basically combining this work from this improvement from 17 with the skip scan from 18 to give you a further improvement on your queries. I think I have, oh no. Okay, so that's the only example I had for in. For or, it's similar. So if you have queries with lots of ors, this equals that, or this equals that, or this equals that, it's going to transform the values to an array, and it's filter on any of them. So the transformation will allow you to use bitmap index scans more efficiently. And I've seen reports posted around of 100x improvement. And again, if you have worked with ORM queries, you see that some of them do lots of these ors, lots of these ins with huge lists. So it helps that it can now better work with these. This is another pattern. So I've seen lots of ORM queries generated this way as well. So here's an order. An orders, we have a T1, then it joins against itself with a different alias, and it just joins it, and where T1 status equals completed. So before, you would do some not very efficient plans. So what Postgres 18 does is that it detects this redundant self-join and removes this table, the redundant table, and executes it as a simple select. So and it's going to filter those. So I've seen it many times on ORM generated queries, view definitions, query builder apps. Yep. So I see some people here smirking, so they've shared my pain. So I'll run this quick anecdote. So Crunchy Data, I have a customer that I worked with at Crunchy, and it was a very large customer. It had a very large installation of a software from a partner that I won't name. But their installation was huge. And the software from the partner relied on an ORM, and it generated these very, very, very inefficient queries, like thousands of them. It was crazy. And I've reached out to the partner several times and said, look, guys, you guys have to improve your queries. Just hire a DBA, right? Hire someone, because this is horrendous. But they wouldn't listen. So there was this big emergency with this customer. The Postgres was generating tons of WAL all the time. The system was melting. We had like 10 people on the call, and everybody was like, oh my gosh, what do we do? And the partner basically tried to throw me under the bus, or Crunchy, or Postgres, really, because it said, well, it's the database fault. And I said, no, it's not the database fault. It's your queries that are horrible. Your queries are terrible. You guys, I didn't quite say it that way. But I was like, oh, you know, but here we can improve some things. And one of these times, the partner brought in a developer, one of the developers, and he shared his screen, and he's like, look, I can run this on my laptop, and it works fine. Like, well, yeah, you have like 100 rows, and you're the only client. Yeah, it's going to run really fast. But when you have thousands of concurrent connections, and you have all these things running at the same time with lots of data, it's not going to be the same. And the culprit were these types of queries. You would generate all these horrendous queries with gigantic lists of n values and ORs, and it was terrible. But so I'd be curious to see what happens to this customer once they upgrade to 18. Hopefully, it'll be better, and the partner won't throw us under the bus, or won't try to throw us under the bus again. But it was quite interesting to see happen. So. All right, so again, my test, just a simple self-join. I don't know why 17 did worse, but Postgres 18 was 5 times faster on my test, just by eliminating that self-join. So again, if you have software that relies on these ORM queries or query builder tools, they might benefit greatly from these improvements. Okay, hash joining and group by. So the planner can now choose which table to hash. If you're doing a group by, sometimes it hashes values. So before, the planner would hash only on the inner table. Now it figures out which one it's better to hash at, and that leads to a 40% reduction in memory usage on large data sets. So it can now pick which one to hash on. And it uses the just-in-time compiler to figure out. And it leads to faster hash value computation and improved performance for hash joins, group bys, accept, and subplan hash lookups. So instead of only hash joins, you can also do a hash write semi-join. I think I have an example. Yeah, I do. So an example that I have here would be if you're trying to find the flights with 1 ticket sold. So you have this flights table, which is joining against this ticket flights. So obviously you have the flights table is larger than the flights table. The ticket flights is larger than the flights table. On 17, you'd use a hash semi-join, and you would hash against the larger ticket flights table because it's the inner table. But on 18, you can figure out if it can use if it's better to use flights or ticket flights. So it was 50% faster with 40% less memory usage, just because it can now figure out which one to use. So it's quite nice for group bys on 18. Okay, so explain improvements are not really performance improvements, thank you, but it will help you improve your performance. So in 18, you have automatic buffers when you do explain analyze now. If you do an explain analyze verbose, you get some hardware stats, some per connection stats. So that gives you better observability by default, so you can do better troubleshooting. So an example here, if you do an explain analyze on orders, you see your buffers here. So that's by default now when you do an analyze. Before you had to add the option here for buffers, but now it's by default when you do an analyze. Other examples, if you do, you have a memory now, so and you can get more information from indexes. I had to break this up into lines, because otherwise this would cut off. But you get the output, you get the number of index searches if you're doing skip scan. If it decides to use skip scan, here's my memory, how much was allocated. So it's giving us more information so we can better analyze what to do and figure out what to do with our queries. So notice that I add a wall here, but obviously it doesn't generate any wall because it's a read query. But if I do this one, just a simple insert, it shows me my I/O timings. It also shows me my wall records, so 100 records at 5,900 bytes. Gives me more output here. And I asked for memory, so it showed me the memory here that it's allocating. So it's just a quality of life improvement. Gives you more data. You can export that to JSON. You can do different things. So I imagine tools will be able to take advantage of this new information and hopefully help. Maybe AI, somebody will come up with an AI system that will work with this information. But to me, it's a nice quality of life. I don't have to ask I can ask for more information, but it's also showing me more information as I go along. So that's explain. All right, does anybody know about UUID v7? Anybody worked with it? Okay, we have a few hands, very nice. So UUID, the v4, it was completely random. You had poor index locality, and it led to index bloat and fragmentation. So as your table grew, the inserts could get slower. So what they did with UUID v7 is that they put the first 48 bits as a timestamp, and the rest with millisecond precision, and the remaining bytes will be random. So it's time ordered, but it's also globally unique. For us, the database guys, that leads to better B-tree performance and lower disk usage. So if I create a table, and if you create a table, you decide to use UID, use the new function, UID v7, and when you insert, the inserts will naturally be ordered by time, and you can infer the creation time from the new UID, whereas you can't do that with v7, with v4. So on my test, this is the difference, with 23% smaller index. So I had the same number of rows, UID v4, UID v7, so I had 23% smaller index on the UID v7 data. Range queries, I had significant improvement here on when I was looking for something in the middle 40%, but I also had improvements on if I was looking for the last 10%, or for doing a limit was, the scale wasn't quite nice, but it was quite an improvement. So it's going to be faster for larger result sets, so that better index locality is going to improve sequential scans. Most beneficial for queries returning many rows, and excellent for time-based queries. It's not all roses, though. I noticed that if you try to join, and again, it could be my not very professional tests, but I've seen this pattern where somebody creates an ID and an event ID, and then they try to join the two, because basically some UUID joining against some other UUID. That wasn't so good. So it seems to me that, at least with v7, if you need UUIDs and they're sequential in nature, do use it because you're going to save a lot of space and it's going to be faster to query through them. But if you need to join them, evaluate to make sure that it works well for you. I think we're coming to the end. Okay, statistics. Major version upgrades. Who hasn't had to spend some time after an upgrade? Oh my gosh, we did a major version, we have to rebuild the stats. 18 helps you with that. You can now migrate statistics. You don't have to wait for auto vacuum to collect. You can preserve query plans. You can copy production stats to dev and test. So if you do a PG dump and you do a statistics only, you can now get all of these things here that you can, there's these new functions, restore relation stats, restore attribute stats, but it gives me all my nice statistics. So you can dump from one database, let's say your production one, import it into your dev test, and you can run, at least try to run with the same kind of planning, or give the same data for the planner to work with. So that's very nice. Okay. So, how many? Okay, I think I'm good. I don't have to run as much. I wanted to run some stats, some benchmarks with real applications, so I picked 4. I picked GitLab, Discourse, Odoo, which is a Python CRM, ERP, and PostHog. I had issues with both of those, coming up with tests that would give me good data, so I decided to not include the images, but I used GitLab. So in my GitLab tests, I had about the same number of queries between all 3 versions, about 14,000 queries, but my total query execution time was quite a bit lower on 18, about 54% actually, compared to 16. So consistent number of queries. And on Discourse, it's a forum software, but again, similar number of queries, lower execution time, but not as significant, 14%. On GitLab, I used its API to generate pull requests, merge requests, create a lot of things, query a lot of things. And on Discourse, I was just creating topics and posts and then querying those. So it was faster, but I changed nothing in the applications. So free performance and consistent number of queries between 3 versions. So real world use cases, who do I think will benefit the most? Analytics, so async IO and optimizer, the optimizing improvements are going to make those better. SaaS applications that need to rely on UIDs can now use V7, lower disk space. Skip scan is going to be important for those. E-commerce applications that might need JSON, and you can now build parallel indexes, GIN indexes. All the optimizer changes we saw can also help those. Content platforms that use full text search, parallel GIN index builds, multi-tenant apps that rely on maybe a tenant ID index. Now skip scan will be able to help those. So, key takeaways. Postgres 18, measurable performance gains. These gains are mostly automatic, so you don't have to change your applications. But if you test, you can probably find more opportunities to improve based on these changes. Async IO is foundational, so we're probably going to see a lot more work going forward. Right now, async IO is only for reads. Maybe we'll see them for writes, I don't know. I'm not that deep into what the development team is working. Skip scan brings those acceptable performance for multi-column indexes on queries that are seldom used or seldom run or less frequent. Parallel GIN brings those faster index builds. And the optimizer gives us smarter query planning. So quite a packed release, lots of good stuff. Some additional resources, the release notes, of course. Tomasz's post was super helpful. There's a deep dive on PG Analyze. There's this blog post from Crunchy that was helpful. This slide share from Jonathan and Peter was super helpful. So I borrowed some info from them. But so do take a look. And this is the feedback QR code. Please do leave feedback. And these are the slides, again, from the beginning of the presentation. And I'll upload to the conference, the conference system. So with that, I'll open for questions.
Questions? May I add, don't use ORMs.
Yeah.
Yes, don't use RM. So thank you so much. I was looking forward for this presentation because it's my
I'm glad.
narrow topic of interest. And I think my question is related to the feature which rose the most interest from audience about avoiding extra like self-joins. Because it's like everybody were happy because it's common problem. So my question is though, can you kind of quantify to which extent PG18 can like remove it? Because there are many non-obvious issues how people abuse and the example which you showed was kind of like, yeah, but I mean, people are creative. Users are creative, ORMs are also stupid but creative. Like I'm just curious, any kind of measures of when it would and when it would not?
That's a good question. I didn't run, that's a good question. I should have run some more tests on that. So I didn't. I don't know if you have lots of self-joins. If it'll try to remove, my gut feeling tells me it will, but I didn't run any tests. But that's a great, I'm gonna go modify my, and try it out.
For next presentation.
Yes. Thanks, Henrietta.
One of the main reasons to use random UUIDs is to not expose private information, like when an account was created or how much time had passed between two records. It seems like this is kind of giving you it's giving you the best of both worlds for performance, but the worst of both worlds for security, because it's like a sequential ID, but it's exposing information, but also not giving you the
Yeah, it'll expose that you'll be able to tell that one came after the other or before.
Well, and how many milliseconds occurred between them.
Yes, but that's pretty much what we know. Now, UUID v4 is still available. You can still use them. It'll be up to you to determine if the trade-off with v7 is worth the limitation that you just mentioned. For some people, it is. Like if you're writing time series data and you just read, it's just basically an event ID, and you're generating billions of them, so you can't just do an int or a big int even. That's an acceptable trade-off. It's going to give you benefits, but you don't really care if you can infer the timing.
Still like 64 bits of random.
Yeah, but you can infer the time from the UID, but it'll be based on your requirements. But it's a good question. Thank you.
Hi, maybe a simple question, but the UUID v7, will it benefit also for Brin indexes on them? I'm not sure if there's a reason for it, but...
I don't think so, because Brin is mostly for scalar values, so you should probably use GIN index for those.
Okay, thank you. Nice talk, by the way.
Oh, thank you. Thank you. Appreciate that.
Thank you, nice talk. Will the async IO improvements in 18 bring any benefits for table partitioning in Postgres?
Probably all of those will help with table partitioning. I wasn't looking for use cases specific to that, specific to partitioning, but skip scan and the optimizer improvements will probably help you with all of those, because when you're querying a partition, you're querying a specific table. So all of those improvements will still apply to a table. I wasn't focusing on that on this talk for I'm sorry, I wasn't focusing on partitioning for this talk. I mostly wanted to talk about the performance improvement, so I didn't look for those, but it's a good question.
Thank you.
Okay, one last.
Yeah, could you, on a very high viewpoint, give some insights on the challenges of implementing async I/O for Postgres 18? Because other proprietary database systems have had that for like decades, and I was curious if you have some high level. I want to say the word high level. I forgot the word. So could you get some insights on that?
Sure. So obviously, the folks who worked on it, Andres, Melanie, Thomas, they had that YouTube video that I mentioned. Andres goes on in depth on it. Basically, it's a hard problem. Postgres has a multi-process model, so you have to coordinate these things between different processes. It adds some challenges when you're talking about a multi-threaded process where everybody has the same memory. So it took a long time to get it right with that coordination. Postgres values the multi-process model. Other databases prefer to share memory. But basically, it was a hard problem that it's hard to get right. So I think that we'll see improvements now as we build upon this foundation. But for information on why it took so long, you probably best refer to the very smart folks who worked on it. One last thing I want to say. We don't have time for more questions, right?
One thing, Andres will give talk about AI tomorrow at 13.
Okay, excellent. All right. So I just want to say that Postgres is an amazing project. I have a lot of fun and working with this community. Thank you all for coming and being here today. I know everybody's time is valuable, and thanks for being part of the Postgres community. So.
Okay. Thanks a lot.